Freidus. Welcome to my second installment of videos for the AP Chemistry class. Mr. Freidus here. Hopefully you figured that out. Anyways, I hope you get a good laugh out of all this. I know you're enjoying that. But anyways, I'm going to work on my okays, my all rights, and my so's. I'm going to try and be a little better, but you know I can't help myself. Today I want to talk about a couple things. We want to talk about overlap with bonding, and then we're going to talk about hybrid orbitals. So this follows the notes that you should have taken in your note guides from the molecular geometries and electron domain geometries. This kind of follows suit along the same ideas. So anyways, you can read what's here. Covalent bonds formed through sharing of electrons by adjacent atoms. All right, this can occur only when orbitals on the two atoms overlap. So in order for covalent bonds to form, you have to have some kind of overlap between the two atoms, as you can see here. These two atoms have some kind of overlap where their shared electrons can exist. All right, here's a different one. Let me get my pointer going here. Over here you can see that this is a p orbital bonded with an s orbital. If you think about it, hydrogen's only got one s electron, and chlorine has the 7 or the 5p electrons, and well, I should say the 2p5 electrons in the p orbital. And there's chlorine with 2 of those combined together, so the p orbitals, the peanut shapes is what I called them, if you remember. And notice they all have overlap. That is where the covalent bond forms, in between where the electrons can be shared. Who's keeping any of the 3 words yet? Remember this graph? There's the elephant. He's annoying. Anyways, basically there's an optimum distance between atoms where electrons can be. If they're too far apart, they don't bond, and if they're too close to each other, they don't bond, because the nuclear charge of the two atoms will push them apart if they get too close. So there's I think it's going to say it here. More overlap brings electrons and nuclei closer, but if atoms get too close, you can think the internuclear repulsion, think of that as the nuclear charge from both of the atoms, the positive nuclear charge of the two atoms pushing each other away. So we're going to talk about 2 different ways orbitals can overlap to form bonds between atoms. The first is what we call sigma. A sigma bond is just a single overlap. Notice it happens in a linear. I believe they're going to do it for me, so I'm not going to do it. And then the other is pi bonds. All right, so notice we have the 2p, or it might be 2d's orbitals overlapping. Notice the linear formation here. This is going to wind up being some kind of other formation. So these are all sigma bonds. Sigma bonds are characterized by head-to-head overlap. So you only got, they just hit head-on and they overlap one time in one place. This is what's important. All right, if nothing else, this is what you need to remember right here. Single bonds. So in any single bond, we're talking about a sigma bond. Sigma bond. I'm thinking about insurance, not sigma. So that's the key. And then this is what I was talking about. Notice the linear relationship. You can draw a line straight through the nuclei and the bond itself. You can see that. Okay. Here is pi bonds. Again, we've got the two. Let me get my pointer. We've got the 2 p orbitals in this shape, peanut shapes, overlap twice. You've got one overlap here, one overlap here, side-to-side overlap. These occur only in double and triple bonds, so we'll talk about that in a second, but they do not occur. And here's what you need to know. If nothing else about overlap, this is what will be on the AP test. If you're talking about a single bond, like I said, you're talking about a sigma bond. That's what a sigma bond. If we're talking about multiple bonds, I need to be clear, multiple bonds, the very first bond that is formed in multiple bonds will be sigma. So if you see the yellow lines here, that means you have one sigma. That will always be the case for double bonds, and that will always be the case for triple bonds. So no matter what bond, single over here, double or triple, the first line that you draw is always representing a sigma bond. Sigma bond. So in double and triple bonds, all of the other ones are your pi bonds. So that you've got, over here you've got one sigma and one pi bond. Over here you've got one sigma and two pi bonds. Usually the questions on the test are as simple as that. So you have to know what the structure looks like, and then they'll ask you how many sigma and how many pi bonds you have. This is really a pretty easy topic once you get that. Okay, so here's our second. I said okay. I don't know how many times I've said it. Who's keeping count? Well, here is our hybrid orbitals. This is the second topic I wanted to talk about, and I'm going to be completely honest. Some of this stuff I'm a little fuzzy on, so maybe someone can help me out and do some research and explain it to me. But I can get you through what you need to know for the AP exam. All right. So let's talk about beryllium. All right, here is the, I said all right. So I've only counted two. Where are you guys at? Here's the electron configuration for beryllium. Hopefully you can get that. You've got 2 electrons in the 1s2 and the 2s level. What it's going to say now is now you're going to hit it with energy, and you're going to move one of the electrons from the 2s into the 2p. We call that an excited state, if you remember. It's not where it's supposed to be. You should be able to recognize that this electron configuration represents beryllium in its excited state, because you have an empty 2s with electrons moved all over to the 2p already. Okay, so this changes what our orbitals look like. All right, it's no longer just s, p, d, and f. We have these hybrids. So their wording, the way they do it is, this means there are 2 degenerate sp orbitals, higher in energy than the 1s but lower than the 2p. So you've got something kind of in the middle. You've got something in between these two. So remember, s orbitals are sphere-shaped. P orbitals are what I call peanut-shaped. You've got a mix of those in between that's kind of more energy than over here, but less energy than over here. And since you have 1 electron and 2 electrons, they're calling that 2 degenerate sp orbitals, sp being the mix between an s and... I'm going to give you a bunch of drawings, and this is where I said it gets a little fuzzy for me. I don't quite get how it all works out in my head. Maybe, like I said, maybe you guys will get it better. But here's your 2 degenerate hybrid orbitals. Okay, it's not an s, it's not a p, it's something in between, and then you put them together. Well, they're saying 2 lobes like p orbitals on each one of them, but one of the lobes is larger than the other. Okay, to make the sp hybrid, you put those 2 together. So in the end, when it's combined, you've got something that I believe this is just not a great drawing. You got something that kind of looks like the p orbital, but these, let me get these so-called lobes would be more circular, kind of like the s orbital. My drawing's terrible. Again, as far as the physically understanding what's going on, it's not necessary for the AP exam as far as I know. So if you're like me and you don't understand how that works, I will tell you when it's important. Okay, so there's that. This is one of the prime examples. If you remember, beryllium fluoride was an example of this. All right, so now they're moving to boron. So let's see the ground state for boron. It's going to have one more. Okay, it's going to have this. Let me get the pointer. It's going to have this additional electron here, but when we put it into its excited state, okay, now we move one of the 2s electrons into the 2p level. The result is now we're going to have 3 of our hybrid orbitals. Okay, so if you look, you've got 1 that's in the s and 2 in the p, so that's how they put the notation. They call it 3 degenerate. 1 is an s and 2 of them are p's. So we've got an sp2, and that's what you need to know. You need to know that if we're, by looking at the geometry, if you've got just 1 in the p and you're going to move 1 up, that winds up with 2s, with an sp2, I'm sorry. All right, so here again are the drawings. Hard for me to keep up with how this works and how they come up with the drawings. I'm usually good at those things too. Okay, and you get basically what you get this time, the result is instead of having 2 peanuts or one s orbital sphere shape, you get this like 3-leaf clover looking geometry. All right, this is your sp2 hybrid. It's not an s, it's not a p, it's something in between. All right, this happens with our, this will happen with, we're going to learn it has to go with molecular geometries. The previous one with beryllium was linear geometry. What geometry is this? Molecular geometry. We're looking at trigonal planar with 3 electron domains. That will always have an sp2 hybrid. This is the electron domain geometries. All right, so next we're going to do carbon. Here's your ground state for carbon, and we're adding 1 electron. We hit it with energy, and we move 1 electron to the empty p orbital over here. And now if you look, we've got 1, 2, 3, 4. We call that 4 degenerate sp3 orbitals, SPPP for sp3. Does carbon typically form? I'm not sure about this slide. Well, I guess we need to look at that slide. Let me go back. Can I go back? All right, won't let me go back. Regardless, think about carbon. Carbon has how many electron domains? Carbon's going to look something like that. 4 electron domains. Hey, I did that all right. So that shape is tetrahedral. If you remember, the SP we said was linear, SP2 was trigonal planar, SP3 is going to represent tetrahedral. All right, so then we move on, and let's see what happens here. The next one after carbon, oxygen. We move 1 from oxygen, but then where does the extra electron go? There's no... Dude, I went too far. There were no more... See, I can't believe I can't get back there. There were no more spaces in the p orbital, so the last electron moved over to the d orbital. So now we have 1s, 3 p's, and the last electron that got hit with the energy moved up into the d orbital. So we have sp3d, 5 degenerate orbitals. What shape do you think this is going to be? What's the next one that has 5 electron domains? The one with 5 electron domains here. Here, this is going to be trigonal bipyramidal. and then the next electron is going to move into the next D. So when we have that 6th one, I think we're talking about maybe where nitrogen is or something like that. We wind up with 6 degenerate, and we got 6p3d2, which is going to be your what shape? Well, here it is here. It's octahedral was the answer to the last one. But here's what we got. And this is really what you need to study and know. You need to know if you've got a linear shape, okay, something like this. All right. Your hybrid orbital is going to be sp. They put the 2 sp because these are in the, well, don't worry about the 2, but it's there. All right. If you have a trigonal planar shape, you're sp3. All right, and then I'll fill the rest of these out because I already spoke to it. Okay, and this table right here is what you really need to understand. You need to understand the shapes, okay, the geometries, and now we're talking about molecular geometries, the actual geometries of the atoms themselves, not electron domain geometry. Okay, so the actual geometries, and we need to know what hybrid orbital is apparent in those. So we need to know that these two go together, these two go together. And obviously you need to know how do I, really with these problems, the way they'll ask it is they'll give you BF3. You'll have to recognize that that's trigonal planar and that's an sp2 orbital. Okay? I believe that might be it. No, okay, yeah, they gave you one last little chart to look at here. It's hard to see, but it's the same thing that was on the other chart. So that's installment number 2. I hope you enjoyed. I think I did better. I only counted like 2 or 3. Well, I know there's more, but okay. All right. So have a nice rest of your day. Talk to you later.